Say if psi 1 and psi 2 are the two wave functions and are linearly independent, they should satisfy the condition C1 psi 1 plus C2 psi 2 is equal to 0. Here C1 equal to C2 equal to 0. If psi 1 and psi 2 are linearly dependent, then C1 psi 1 plus C2 psi 2 equal to 0, but C1 equal to C2 not equal to 0, which means that C1 and C2 are not equal to 0. In this way, we can classify linear independent and linear dependent wave functions. Now we can introduce a new concept, wronskian. The wronskian is W equal to psi 1 psi 2 dash minus psi 1 dash psi 2. This is called wronskian. Here psi 1 dash is equal to dou psi 1 by dou x and psi 2 dash equal to dou psi 2 by dou x. If psi 1 and psi 2 are linearly dependent, they should satisfy the condition C1 psi 1 plus C2 psi 2 equal to 0 with C1 not equal to 0 and C2 not equal to 0. Now differentiate equation 1. Differentiate equation 1. We can get C1 psi 1 dash plus C2 psi 2 dash is equal to 0. This is equation 2. The equations 1 and 2 are linear homogeneous equations with the two unknown constants C1 and C2. See this, the equations 1 and 2 are linear homogeneous with two unknown constants C1 and C2. Then equations 1 and 2 are linear homogeneous with two unknown constants C1 and C2. These two equations have non-trivial solutions only if the determinant, just take the determinant, psi 1 psi 2 psi 1 dash psi 2 dash is equal to 0, which means that psi 1 psi 2 dash minus psi 2 psi 1 dash is equal to 0. But W equal to, that is wronskian W equal to psi 1 psi 2 dash minus psi 2 psi 1 dash. Now we can conclude that necessary and sufficient condition for psi 1 and psi 2 to be independent is that wronskian does not vanish. That is, W not equal to 0, the wave functions psi 1 and psi 2 are linearly independent. Then W equal to 0, the wave functions psi 1 and psi 2 are linearly dependent.